Hi everyone, my name is Mirko Miko. I'm a quantum control engineer at Q-CTRL, and today I'll be giving the second part of our presentation series on the application of reinforcement learning to the optimization of quantum gates. In particular, we will focus on improving 2-qubit gates. Cloud-accessible devices are becoming ubiquitous and easy to access. However, one of the most critical factors limiting the performance of quantum computers are its noisy gates. If we want to use quantum computers to solve meaningful problems, we need to reduce gate errors in these devices. 2-qubit gates are the basic operation that generates entanglement between the qubits of a quantum computer. They also form the basic building blocks for more complex algorithms. For example, you can see a sketch of the quantum circuit for the variational quantum eigensolver, also known as VQE, depicted in this slide. Highlighted are the 2-qubit gates present in the algorithm. The errors introduced by faulty 2-qubit gates severely limit the current performance of the algorithm. One could try to improve the gates by starting from a physical model of the system, but this heavily relies on having an accurate model. For platforms like superconducting qubits, this is not always the case. This is particularly true for multi-qubit devices, where unknown Hamiltonian terms strongly affect the dynamics of the system. In the figure, you can see the results of a simple experiment where we applied a 2-qubit drive and followed the time evolution of the population of the 4 basis states during the drive pulse. The dashed line represents the dynamic computed from a simulation of the system, where different colors are for different initial states, and the dots are the experimental data. Clearly, the simulation is quite far from the experiment for even a single application of the gate. The question that we want to address is the following. Can we learn good implementations of a 2-qubit gate without having any physical model? One way to do this is to use reinforcement learning. Reinforcement learning is known for its ability to deal with massive state spaces and imperfect information. For example, one of the most famous success stories of DeepMind's implementation of a reinforcement learning agent is AlphaStar. This algorithm was able to learn how to play StarCraft 2 at the highest level of the game, even beating world-class players. These features make reinforcement learning a perfect candidate for gate optimization on a quantum device, where the state space grows exponentially with the number of qubits, and only partial information is available from the measurement of quantum states. We have carried out our experiments on a cloud-accessible IBM superconducting qubit device. The system is composed of several, up to 7, fixed-frequency transmon qubits coupled to each other via resonators. In this platform, an entangling gate can be implemented through the cross-resonance interaction. This interaction arises when one of the 2 connected qubits is driven at the frequency of the other, effectively implementing a ZX theta rotation of the qubit pair. The current implementation of the CR gate is far from optimal. The gate is very long, lasting for almost half a microsecond. Crosstalk between the qubits lowers the fidelity of the gate, requiring an additional cancellation tone, which adds complexity to the control. An interaction between neighboring qubits introduces dephasing. Meanwhile, the control electronics add a signal distortion, which are difficult to compensate just by calibration. Reinforcement learning can tackle all these challenges by learning an optimal pulse through direct interaction with the device itself. In particular, in our implementation of the reinforcement learning algorithm, the agent builds a full pulse in steps, checking at each step what is the state and the reward obtained with the partial pulse constructed until then. More details on the gate optimization process using reinforcement learning are given by Yuval in his talk, part 1 of this presentation series. Key elements in the optimization process are the cost function that produces a reward for the RL agent and which is used to evaluate the quality of the candidate solution, and the learning algorithm used by the agent to formulate new candidate solutions. Important aspects of the cost function are that it quantifies the quality of the solution accurately. This will inform the agent on how to improve the gate, that it is robust to unwanted effects, and that it can be computed efficiently, as it will be called many times during the learning process. We chose to use a repetition scheme for the cost function, where a variable number of repetitions of the implemented gate are applied to different initial states. The reward is then calculated from the fidelity of the implemented quantum state, estimated via quantum tomography with the target one. This method allows to quantify the error per gate accurately, overcoming contribution from state preparation and measurement errors, and it is efficient in the number of experiments. The important feature of the agent are that it can deal with noisy estimates of the cost and state, which is the situation with current quantum hardware, and that it can work with large state space, a characteristic feature of quantum systems. For the choice of agent, a plethora of reinforcement learning algorithms were tried. Among the most successful ones were policy gradient, also called PG, and soft actor critic, also called SAC. Here you can see the progress of the learning process of an agent using the policy gradient learning algorithm on a cloud-accessible quantum device provided by IBM. Plotted are the mean values of the cost for each step as the learning progresses. When the cost reaches a low enough value, we terminate the optimization and obtain the final optimized pulse. On the left, the default pulse is depicted, while on the right, the optimized one is shown. We evaluate the pulse obtained from the optimization process with a repetition test and compare it with the default pulse provided by IBM. In blue is the infidelity of the default pulse for a variable number of repetitions, and in purple is the infidelity of the Q-CTRL optimized pulse. The average error per gate of the optimized pulse is twice as low as the one for the default pulse. We also evaluate the same pulses using the interleaved randomized benchmarking protocol. The plot on the left is for the interleaved randomized benchmarking of the default pulse, and the plot on the right for the optimized pulse. According to this measure, the average error per gate of the optimized pulse is 30% better than the default. After demonstrating that we can generate optimized 2-qubit gates with reinforcement learning, we want to explore other possibilities in improving the gates themselves, like making them shorter. This poses unique challenges to model-based methods, as the amplitude of the pulse may enter a regime where assumptions about the physical model break. Reinforcement learning, on the other hand, can deal with this situation. Another goal that we have in mind is to use the optimized pulse to show improved performance in an algorithm. That's all from me for today. Thank you for your attention.